My name is Nick Lotz at Voxil 51. If you are on this call, you are here for the auto labeling webinar. We're going to take just maybe 1 minute, see if any more folks trickle in, and then we will get started here in a moment. This is going to last about an hour, like maybe 50, 55 minutes. At around the 10-minute mark, I'll go ahead and start wrapping up things from my side, and we'll have a Q&A at the end. The structure of this webinar is going to be a um, series of presentation and demos by me. It'll start off with some motivation, background, what is verified auto labeling, put it in context of the broader industry and the problems that we are solving in the computer vision space and why this is worth solving. We'll then talk about some research that is done around this field and how it motivates the actual features and workflows. So it's going to be a little bit of a combination of science and engineering, probably towards the end, especially more focused on engineering, followed by a Q&A. So thank you for everyone who has joined. Just as a couple quick notes, anyone here on the call will get follow-up materials after this webinar is over. This is being recorded. You will get a link to all resources at the end. In this format, this is like the Zoom webinar format. Use the Q&A widget that you'll find in the Zoom toolbar. You might need to click the three dots over on the bottom right to open it up. I'll have that constantly open in the background. So if anyone has any questions at all, I'll be able to easily catch it and address it then. And again, there'll be an extended Q&A after the webinar is over as well. As I said before, this presentation will include a combo of concepts and demos. It's going to begin with, again, kind of some motivation and research and what am I even talking about when I use a phrase like verified auto labeling. I think we know what auto labeling is. What does the verified part mean? What's the context of all this in terms of training computer vision models? And then again, we'll pretty quickly go into some demonstration as well that you can probably get a little sneak peek at seeing my tab up here in the top right. Again, this is going to last about an hour, about 45, 50 minutes of presentation. Of course, I'll be happy to field questions as I go. Feel free to use that Q&A panel on the right. And then we'll have a dedicated Q&A at the end also. All right. So am I in the right place? Just as a little bit of background. Um, this webinar workshop is ultimately, it's actually not, I should say here, you don't have to have exposure to 51. It certainly helps. It's definitely not a requirement. If you have any kind of computer vision interest or background, this webinar is for you. If you collaborate with a team of computer vision people, or you collaborate on a team that works on machine learning projects at all, or if you just have either a science or machine learning engineering background, and you either want to understand how to push model performance forward, or if on the engineering side, you want to simplify and automate your computer vision workflows. This workshop is actually about two different things. It is focused on using 51 as the tool of choice for the auto labeling and zero shot labeling and QA stuff that we'll be talking about. At the same time, it is also focused on concepts and sort of a little bit of theory as well, in the sense that the goal is, okay, what is the state of the field in terms of being able to use foundation models for labeling? What are some best practices and recommendations that we have discovered? And ultimately, how do you use automated labeling workflows with other QA workflows in order to improve your model development process. This is not an in-depth computer vision theory course. It is not focused on Python programming. It is not a survey course of the 51 platform. It really is focused on auto labeling. All right, so this is the workshop agenda. We're going to talk a little bit at first about data and models. You're probably, if you're on this call, you might be familiar with the concept of model-centric versus data-centric AI. That might not be a new concept for you. We'll talk a little bit about the history and kind of the delicate dance that data and models have had together, particularly within computer vision. We'll talk about how is the role of foundation models and vision language models affected and to a large extent moved forward our ability to not only train and fine-tune models, but also improve other aspects of the development process. In our case, it'll be labeling of data so that models can learn and be trained off of it. And then we'll specifically talk about that computer vision label problem. Why has it been such a bottleneck? Why has it been so, why has it had to be so manual, even up to this point? How might we improve the process? And that's where we'll start bringing up auto labels versus human labels. We'll learn that auto labeling is not strictly a new concept, right? These foundation models and especially zero-shot labeling have been around for a while now, whether it's open vocabulary or fixed vocabulary models. But at the same time, we'll kind of synthesize some of the insights and learn, okay, if we are introducing a more automated approach to labeling, even if we take a human in the loop approach later or throughout the process, what are some ways that we can optimize and make the process as efficient as possible? And then lastly, we will actually look at it. So we have built a feature here at Voxil 51 as part of the 51 platform that we call verified auto labeling. Again, the goal is to integrate the automated annotation into your overall computer vision development process in a way that is integrated, but also reviewable and QAable and also, keeps humans in the loop for when actual, human intervention needs to happen. It's not just, one-off zero-shot labels and then just take it as it is. The idea is we can fine-tune the process. Who am I? I work in technical marketing at Voxel 51. I'm kind of a hybrid role of engineering and also marketing, trying to make the value of the things we develop here understandable to the technical community at large. I am based in the Nashville, Tennessee area in the southeastern United States. Strangely enough, my background is actually in chemistry and physics, which is actually what first gave me exposure to machine learning theory and practice in general, especially when you are in the hard sciences, you arrive at a lot more constraints sometimes, where, especially in like computer vision, you need to uh, tweak models and tweak architectures in a way that you can't just fake the results because ultimately there's lab results that you need to replicate. I was also at previous companies like GitLab and Harness. Those are more in the DevOps and infrastructure space. I've currently been at Voxel for close to a year now. Just real quick, I always like to show this slide because I work in front of a computer all day for my day job. When I'm not at my day job, I like to go climb mountains and take nice pictures. So if you are wherever you might be based, if you ever find yourself in these areas of the United States, highly recommend these hikes. These are all taken off a cell phone camera. I'm by no means a professional photographer. These are just how nice the views are. Okay, so we're going to go and we are going to get straight into it. And we are going to talk through data and models and what is the delicate dance, as I mentioned before, between what we call model-centric AI and data-centric AI. So the computer vision community has historically pushed model performance by inventing bigger and better model architectures. This has been the case. We have moved well beyond the expert systems of the 70s, but more recently, deep learning models have improved the way that data is incorporated into model architectures theoretically, but still a lot of the focus has been on improving model architecture, even if the models themselves kind of ironically have become more of a black box over time. At the same time, we still suffer from the garbage in, garbage out problem. Research suggests that around 80% of model problems are rooted in data issues. Again, garbage in, garbage out. There are a lot of optimization you can perform in fine tuning to help models perform better against a very specific problem or domain. However, where data issues really tend to rear their ugly head is when you try to generalize models. Well, obviously, we are now in a world of foundation models where we want models to be increasingly generalized. We've also found that in general, the larger the data set a model is trained off of and the more representative the data, the model tends to perform better in all sorts of domains, even if it's not the specific domain it may have originally been trained or architected for. But ultimately, you need both. You need both a good understanding of what constitutes a proper model architecture, and you also need a good understanding on what constitutes a proper balanced representative data set. So data-centric AI is not a term I invented. It's not a term Voxil 51 invented, but it is something that Voxil 51 really takes to heart in how we develop our products and how we think about computer vision. It reframes computer vision applications as an iterative loop. And again, this might be somewhat commonsensical, but we really want to focus in on all of these as important steps. So we curate data sets that we train a model off of, inspect errors, and then repeat the loop. So we're constantly trying to iterate on our data sets, not just the model architecture, right? Often data is not treated as an afterthought, but it's often treated as like fixed. Okay, the data is what I have, and I can't really change it. Well, you can through augmentation, synthetic data, class balance, um, examination of data quality issues so that you can um, augment the data set with edge cases if needed to improve model performance. And our goal here is to ensure that data is always side by side with whatever improvements we're making in our actual models and visual AI applications that we're building. So each iteration on any of these on both data and models ultimately improves both sides, right? Better data leads to better models, but improved model performance, especially when the models are bigger, faster, that can also improve our ability to pull in increased and better data to further push the model. When it is more efficient and cheaper to curate better data sets as well that are properly labeled and balanced, that also means we can redirect resources into training bigger and better models as well. So the catch here, though, is data curation really is the bottleneck, right? GPUs, just due to Moore's law and all of its variations, compute power has, gone steadily down, but human labor costs have not. So the human labor involved with curating data sets are the most involved and costly step of the data curation process. And these are just a couple of numbers that we have found here where, if for example, on a Cocoa style or Cocoa scale rather data set, it could take about, 7,000 human hours and hundreds of thousands of dollars to draw the amount of labels needed to train a computer vision model. To just hit home the point here, computer vision, right, is very specifically dependent on human provided ground truth, right? It's not like large language models where they can self-supervise based off predicting text tokens. We are telling the models what the truth is in terms of the data set, and that requires us initializing that ground truth in the first place, which takes a lot of time when we're trying to create data sets at the scale needed to train our models, especially train the models that are really pushing the boundaries of how performant visual AI should be. So closing the data gap matters just as much as closing the model gap. They are at least equal in importance. And this is sourced from an MIT course called Data-Centric AI. This is not a pure XKCD comment. It is a comic. It is inspired by XKCD. But again, just as a little bit of humor, the idea here is that data is the core fuel needed for model development, and the quality of the data will often represent a floor on the quality of your model. All right. Okay, just a little more history here. So where do foundation models come into play? Well, again, remember that data labeling is the bottleneck. Historically, that has meant large companies employing fleets of human contractors to label data, whether it is general or often domain expertise data, medical, manufacturing, auto, agriculture. However, the rise of foundation models and specifically vision language models have allowed for increased generalization on this point. So starting in 2021, when OpenAI released the CLIP model, and then particularly in 2023, when Meta released its segmentation model, we started to realize that open vocabulary models, that is, models that can generalize any class prompt and can have pretty good performance on arbitrary data sets. Now, obviously, there are limitations the more specific you get into a given domain, but just like with large language models, vision language models are improved every week, right? They are getting better at accurately identifying elements in visual media, particularly static images. They've gotten quite good. Now, again, in fixed domains, fixed vocab, or rather in more specific domains, fixed vocabulary models still often have the advantage in which when you have models trained off very specific classes, then they can be better at identifying those classes on a given validation set. But foundation models are getting better every day. And what we're ultimately finding, just to give you a preview of where I'm going to be taking this conversation, is that as a first pass in particular, uh, zero shot, open vocab, off the shelf foundation models can be very, very good at giving you a solid set of labels up to like, the 90 to 95% um, of your data set. And obviously that 5%, or less still might need like human labeling, but at the same time, you save a ton of money and resources and effort by focusing on the edge cases that need that extra human attention, while at the same time training downstream models that have quite good performance based off the labels generated by foundation models, what we call auto labels. So remember that object annotation still lives and dies on labeled bounding boxes. So hand drawing them is slow, expensive, error prone. There's been a rise of annotation vendors that can charge millions because, in their view, more labels equals better models. You charge by the label, it becomes this whole economic model. And at the same time, and because of this, teams tell us that annotation pipelines are really what is causing this bottleneck, both in terms of cost and in time. And there's a lot of numbers on this table. What I really want to point you to is this second row from the right, the cost of annotation that it would take to label some of these core like data sets as a function of the number of objects you're labeling and the number of hours it would take. And then just to give you a preview, if you're like letting computers do the work, letting an off-the-shelf foundation model do the work, the accuracy we'll see in a little bit can be quite comparable at a fraction of the cost, orders of magnitude less. So in terms of motivation, again, it is zero shot labeling is not a brand new concept. However, it is increasingly becoming viable as a replacement for human labeling for a large part of the labeling cycle. By no means are we advocating at this point that in isolation, you zero shot label all of your data and do no other any kind of human in the loop QA. That's why we're introducing a workflow that we call verified auto labeling. The idea being here that it is still automation first. It is integrated as a core part of your data curation workflow and ultimately your model development workflow, but it's part of a larger of larger platform capabilities like model metric evaluation and embedding visualizations and data quality metrics. You have the ability to very quickly iterate um, off your auto labels that we find already have a pretty good base of accuracy. So real quick, we're Voxil 51. We developed both the research that I just talked about a moment ago, uh, a paper we introduced called Auto Labels for Object Detection. We are the lead maintainers of the 51 machine learning tool set. Our approach is really a data-centric AI approach. Our goal is to maximize building better AI applications by improving your data. You'll see this in the UI immediately, where your data is side by side with everything you do in terms of your development process. And again, our theory here is that, or rather, our hypothesis and what motivates us is that you can't out-train bad data, right? Regardless of how good your model architecture is, garbage in, garbage out. Often the easiest way to move the needle is improving the quality of your data set. So what are some of the things we're going to include here? So in a little bit, I'm going to drop into a demo and I'm going to show you this process of within the 51 platform, auto labeling your data sets. As I said before, simply running a model and generating labels is not the end of the road here. Right now, pure foundation models are not good enough to really give you that 99.9% label accuracy that really allows for model performance to be maximized and optimized. It can get you to that 95% plus, but you still need verification and QA steps to improve and fix the occasional label errors and just make sure that everything is as accurate as it can be. So auto labeling is going to take place side by side with some other built-in tools on the 51 platform. For example, dataset curation and visualization. So here we have a human faces dataset on the left. Side by side, we have just a bar graph of the class distribution that's in the middle, and then on the far right we have the embeddings visualization. In this case, color coded by confidence score. Where embeddings becomes really useful, particularly for um, auto label verification, is it gives us a very easy visual way to examine outliers and see where do our labels need extra attention, where may have they made mistakes. Classic example. In a little bit, we are going to be in the Berkeley Deep Drive data set, and a very common zero shot um, label that gets applied is if you say, hey, label a car, it'll often label the ego vehicle. Like, from the perspective of the camera, it'll label like the hood of the car, of the point of view car, as like a separate vehicle. And that might show up as like a separate section of the embeddings. And you can very easily lasso that section and tag those labels for like review or deletion or to be fixed. Yes, sorry, I see the question here in chat. This will be sent out to all participants on the call. I'm not sure if we have plans right now to immediately upload it to YouTube, but you will receive a copy of this recording sent out to everyone who registered for the webinar. So again, one method that's going to be crucial here is visualization as part of a broader data curation effort. Second is going to be quality metrics. So this is particularly important for reviewing edge cases that might cause model failure modes. For example, maybe you have an automotive model and it doesn't perform well in like bright, glary, maybe snowy conditions. Well, having a sense of what is your data balance reflective of those conditions can be helpful. Well, right in the UI, we have a data quality workflow that computes metrics like brightness, blurriness, entropy, near and exact duplicate samples, and a couple others. And you can very easily just use the slider to isolate where in your model, or sorry, where in your data set you might have your distribution of this particular metric. So for example, in terms of brightness, we have a rather long tail of not very many bright samples, right, compared to the rest of this distribution. So we might find that we might want to augment this data set with additional samples to be reflective of this edge case that might be causing model failures. And then finally, model evaluation is obviously among the most critical. Ultimately, our goal is to build better models. When being able to examine and compare model performance, metrics like F1 score, precision, recall, obviously those classic metrics, but also class-specific metrics is going to be critical as well, especially when you're increasing the amount of automation, in this case through generating auto labels. It can be helpful to know if I label a data set with auto labels and I later train downstream models, where are those models succeeding and where are they failing? If models are not performing well in particular classes or under particular conditions, can I go back and check my performance of my zero shot labeling and see where they might be failing, right? Is the problem on the labeling side or on the data side where there is like maybe low recall, for example, of certain classes that therefore is not being that therefore is causing issues, when I'm actually training off those labels later. Now, again, the goal of all this is you have all of these steps together and available kind of within a single interface, um, where you can constantly go back and make changes to your data set if needed. All right. So going back to here, I showed this table before. Verified auto labeling is integrated with all of these other workflows. So it combines foundation model labels with the built-in QA steps that I talked about here. You can choose, and we'll show this in a moment, from off-the-shelf zero-shot or fixed vocabulary models. We currently support classification, object detection, and segmentation tasks. And then when you kick off the auto labeling process, you specify what are the class labels that you want to label, that you want the model to set on your data. And then you can also set a minimum confidence threshold that you can adjust later. Um, the confidence threshold is an interesting discussion because we have found that it can actually benefit you to choose a lower confidence threshold that you initially might think. Like we're talking the 0.3 to 0.5 range or the 30 to 50% range, depending on like what exact, metric you want to refer to. Um, Basically, maximizing recall, um, even at the expense of a little bit of accuracy, can sometimes result in better performing models down the line. In our internal benchmarks, verified auto labeling hit about 95% of human downstream model performance, again, while slashing costs by orders of magnitude. And I have this graph to show in a minute on the performance front. I showed this table before. So we see that in terms of human supplied ground truth, when we are training downstream models, auto labels perform very well comparative to human ground truth. The research powering this feature is a paper we released called Auto Labeling Data for Object Detection. This paper was just released a couple weeks ago, and you can find it on archive.org. And the methods we used are we used a foundation vision language model to label a training set. That's part of the feature we have available that I'll show in a moment. And then based off of those auto labels generated themselves, which were themselves generated by a vision language model, we then trained a light detection model only on those auto labels. So no human labels were involved in this training. And then we evaluated the detection model against a separate validation set. And then we also trained another detection model based off only human supplied ground truth labels. And then we compared the performance of both models. Um, and then we ultimately validated against 4 public data sets. So VOC, Coco, Elvis, and Berkeley Deep Drive. And then that helped us create a benchmark of cost, label quality, and then importantly, downstream model accuracy. That is, are we not just getting accurate labels, but regardless of how accurate the auto labels were, what is the effect on downstream models trained off of those labels? And the effect was something like this. Now, this plotted on the x-axis is a confidence threshold of the auto labels. So that is when we were when we were generating the auto labels, what was the minimum confidence threshold? And then the mean average precision is the y-axis. The dotted line are the human label is the human labels. And then the color-coded lines are the different foundation models we use to train the auto labels. And ultimately, what this is showing is based off the different models we use to generate auto labels and the minimum threshold we chose, how well did downstream models, in this case YOLO 11N and YOLO 11S, that were fine-tuned based off or that were trained off these auto labels, approach the accuracy of the same downstream model if it was just trained off human labels. And the lesson here is that when we chose a rather moderate confidence threshold, we could get within 90 to 95% here. We could reach this optimization point of approaching the accuracy as if the model were trained off of human labels. You will notice that as your confidence threshold approaches 1, recall obviously gets much lower, and then the relative performance of models trained off auto labels gets much lower. So this is kind of the sweet spot that we found. So this is a good takeaway graph. And just as an example of that, right? Especially when there's like massive amounts of objects of a given class in an image, we found that zero shot and auto labels, especially with a moderate confidence threshold, can perform better than human labels. So for example, when you have all these like donuts in this picture, there's like occlusions, they're kind of overlaid over each other a bit. Um, we found that, in some cases, auto labeling had better performance. And even if you have, a lower confidence threshold, which can increase your false positive rate, the increased recall still balances that out in terms of good performance when you're actually training off of these labels. All right. Okay, so we are now going to see this in action. So the workflow that I just described, I'm now going to jump into 51, and I have this subset of the Berkeley Deep Drive data set here. It's a 10,000 sample subset, so it's not the BDD 100K, it's an order of magnitude less, um, just in terms of being able to take enough time to auto label this set without it taking days. And here we have right now raw data, and in the background, I have run auto labeling already, just due to the time that we have on this webinar. But currently, I don't have the labels like selected in this pane. So like pretend these are just like raw samples. They have not been labeled yet. Now remember that auto labeling can be zero shot from the beginning if you'd like, using either a zero shot or a fixed vocabulary model. So just from having my data set here, might take a minute for this to load back up. You can open the auto labeling panel, put it side by side with your data, and then run an auto labeling job. Now, here I've run 3 different jobs already, which creates 3 different label fields that I could apply. Each of these were of slightly different classes and different models. There is a review flow that goes with this. So if I was starting from the beginning, so maybe depend I haven't run any of these tasks yet. Let's say I am doing this for the first time. I can click this auto label button, and then I can choose first, what am I labeling? Am I labeling the entire data set? Am I labeling just a current view? So maybe I have like some specific filters that creates a view of maybe like, a percentage of this data set. And I might only label that view. Or I could select specific samples and choose only to label those. And then I choose my task. Now, based off the task that I choose, classification, object detection, segmentation, 51 will suggest a foundation model against that task. So right now, in this this is a new feature. Right now, we suggest and offer the models that can be used to perform the labeling task. So in this case, maybe detection, right? This is Berkeley Deep Drive. We can apply bounding boxes. We can choose from a zero shot model in which we have YOLO variants, OWL, and again, we have a few recommended ones, and then the list of all of them you can choose from here. And these will change based off of the task that you choose, right? Are we doing segmentation, detection, or classification? You can also choose a fixed vocabulary model that, again, is fixed in terms of the number of classes that it's trained off of and will label. So what I did in the background is I chose a zero shot model, and I did one run of YOLO World. I did one run of OWL. And then when you but if you're choosing, your initial auto label run, you would choose one of these. So maybe like YOLO World. And next you define your zero shot classes. What do I want to label? Now, because this is a zero shot model, you can include anything here. If I was choosing a fixed vocabulary model, you would choose from like the list of classes that it has available. So maybe I chose YOLO World. Maybe as an initial pass, I might say person, truck, and traffic sign. So these are classes that also have ground truth equivalents, in this case, in the BDD data set. So later, if I'm like, testing this out and I train a downstream model, I could always compare this to human ground truth. Now, again, if you're dealing with raw data, you might not have human ground truth, right? That's why we're labeling this. So you can put whatever, wants here according to whatever standard you put in your labeling schema. And then most critical, but often overlooked, is your minimum confidence threshold here. So this can be set now. After auto label finishes, you can also adjust it later. So what this actually does is you actually get the full confidence distribution regardless of what you set here, but this will be like the initial view that you see after auto labeling is finished, and then you'll see a slider in which you can adjust the confidence threshold after the fact as well. So again, maybe, remember I suggested like a moderate confidence threshold. So we might say the minimum is like 0.2. This is just going to be what do we call the labels? So we might call it, BDD, YOLO, um, YOLO W. And then the run is what is going to be the name of the task that executes in the background. So this leverages Voxil 51's delegated compute, in which if you have any attached GPUs, this will run on those GPUs in the background, and then it'll be part of this run tab that I'll look at in a minute. And then you click auto label, and then you would select what attached cluster you would run this job on. So I've already done this. I've done this exact thing, and this ultimately ran. And just to give you a peek at what it looks like, we can see that I ran a couple of these tasks, and it ran in the background, and it completed. And that's the task that appeared in the review panel just a few moments ago. So if I go back to my sample view, sorry, we'll give it just a minute to load back up. The really the easy step, right? Again, because this is just a foundation model, is kicking off that original zero shot. It's that easy. It'll apply the labels and create the field. Don't know why this is taking so long to load. Let me see if I can give it a second here. Sometimes when my browser resets or I go to a different page, the cache gets deleted and then the tiles need to reload. So we'll give it just a moment here. If for whatever reason doesn't load, there we go. As I say, I have a backup if this doesn't load. Okay, so once a run completes, there's then a review flow that you can perform. So this run here, for example, after I run that auto label step and the zero shot model adds the labels, it gets then tagged as in review. And if I click into it, it'll then say that we found and labeled this many instances of each of those classes that I specified. And then you can also notice that in this case, this confidence threshold is here, but we can readjust it as well. And we also see that it created this label field of what I called it, followed by the in review, with in review appended to it. So I could adjust this confidence threshold and only choose to maybe approve like higher confidence or even lower confidence labels. This will automatically like adjust the labels that are like staged for approval. I could also select individual samples as well. So like if I were to like create a specific view or selection of samples, notice those specific ones will be added for approval. So if I were to say, let's say, for now, I might say all labels of a minimum confidence threshold of 0.2. I'll add those for approval, and then that will get added to my approval tab. Going back here, I've done that on a separate run. And these now are listed as approved. Now, I've kind of skipped a step here. And that step is how do I evaluate the quality of my labels? Like the idea here is like just sliding a confidence slider isn't enough. I needed to evaluate like where may have the zero shot labels been accurate? Where may have they been accurate? Like um, what is my level of like precision and recall? Do I have false positives? Do I have false negatives? How do I identify those? So this goes back a little bit to where that confidence threshold comes in. Part of the reason why we recommend setting like a low to moderate confidence threshold is it maximizes recall. Yes, at the expense of a few more false positives, but false positives are much easier to root out than false negatives, right? False negatives are like unknown unknowns. Like I don't know what my model didn't find. Like I'd have to go back and find all of the missed detections of traffic signs or something. Whereas false positives, it's easier to identify, hey, there's a bounding box around that. That's not a traffic sign. I'm going to delete it. It's easier to kind of QA that process. And one of the most effective ways you can do that is through embeddings. So 51 has a built-in embeddings visualization. If I open up the embeddings panel on this data set, If I haven't computed embeddings already, I can create a new embeddings job and like run the computation. I've done that here already on these auto labels. And if I go here and put it side by side with my data and maybe color by confidence, here's my confidence distribution of labels. And I'll notice, for example, that over here on the right is a cluster of like pretty low confidence labels. Now, I don't know what the class is yet, but if I like lasso that area, I can look at what my auto labels found and I can identify if there are any possible mistakes. So, few things I'm noticing here. Just opening this up with relatively low confidence, it's identifying this bus as a truck. And we might say that, okay, we don't consider that a truck in our schema. Like we would not consider this a truck. This is a bus. There might be a world in which a data set, this would be also be classed as a truck, but in our case, we might say, nope, it's a bus, not a truck. And as another example, I can open another one up. And again, this is showing like construction equipment. It's also thinking it's a truck. Higher confidence, but still. So again, you could see clusters of where do I have low confidence in my embeddings distribution. I can also look at I can also color code by labels. And oh, this is, let's see. Um, let me go back here for a second. I'm going to recompute my embeddings. Not recompute, I'm going to reopen it up. It was trying to layer on different filters here. Give me one moment. IMG val. There we go. Okay, so in this case, this is a little bit of a different example, right? So in this case, we have three different classes. And in my example, the three classes were very distinct: pedestrian, sign, and truck. So like color coding them in this way might not be the most informative versus if you had like car, bus, and truck. But at the same time, you can see like the distribution here. So again, we have like a cluster of outliers over here, which is like interesting in and of itself. So if I lasso this, what do I see here once it loads? We'll give it a moment here. And we can see, this is all yellow school buses, right? That's this outline cluster. And we might decide to tag all of these. Let's see. Yep, we might choose to like tag this entire view as like for further review or even deletion because we might decide, hey, school buses, they're not trucks. And we're not going to train models as if they are. So embeddings is one way in which we can, again, especially if you set a relatively lower confidence threshold and have increased recall as a result, it's a way in which you can kind of QA that process and start to look at outliers and start to get that low-hanging fruit of, okay, what do we know like might have been missed or misaccurately or inaccurately labeled by our foundation models. Okay, so that is one approach. For the next area, I'm going to kind of skip ahead a little bit. And because, we have an hour-long call here, I can't go ahead and like train a model from scratch in the time that we have left. So I am going to skip ahead a little bit and show you just kind of what the end result might be when you're comparing models trained off auto labels. So I'm going to go back to here and, oh, whoops, hold on one second here. Brief technical difficulty. Give me one moment. It's okay. I have a backup. Give me one moment here. Okay, let's see if I can. There we go. All right. So this video is summarizing what I just did, and just going to extend the discussion a little bit. So this is going through the same process I did. It kicks off an auto labeling job. And again, here we tagged all the samples. So this is just a quick review. I might actually increase the playback speed a little bit. Again, we did an object detection job, but the same workflow applies, whether it's classification, detection, or segmentation. In this case, it's car, truck, bus. So, three very similar classes in this video. We run the auto label job. Again, we can adjust the confidence threshold slider to filter which labels we want to review. So here we can see it, in this case, it labeled a bus as a bus. In this case, we just selected three labels for approval. But if we go back here and we go back to our embeddings, let's say we take a broader approach of the entire distribution of data, right? This is actually showing the embeddings computation. So I skipped over that process. I had already done it here. But if we look at the embeddings and we look by confidence, again, we're analyzing outliers for false positives. This is an example of that POV, specifically for like automotive data that I talked about, right? This is what we call the ego vehicle. So that outlier is showing that the whatever model we use for auto labeling, it detected like the POV car, its hood as like a separate vehicle. And that showed up as an outlier because it's like a very different visual image than anything else. And that's something we can tag for potential deletion. Again, nothing new versus what I just discussed so far. What really comes next is when you train downstream models off of the auto labels. 51 includes built-in model evaluation to compare model performance. So this is where we can compare side by side down to specific classes, our performance between maybe different models trained off of the auto labels. Now, in this example, this is comparing a ground truth model with a model trained off of the auto labels. So this is a slightly different case, right? This assumes in this example, we like know what the ground truth is. So this would make sense if you're performing like validation of auto labeling workflows. But here we can see that the ground truth, like the accuracy, recall, F1 score, is pretty close to the downstream model trained off of the auto labels. Now, this is our traditional model evaluation panel that shows these core metrics. We also have a feature that we're going to be introducing here in pretty short order called scenario analysis, which will allow us to go deeper into class-specific metrics. And again, the idea here is we are integrating, increased amounts of like model metrics and evaluation analysis with like the data curation and data visualization that we already have. So in this case, in scenario analysis, we can compare classes like day and night, right? We can create scenarios based off subsets of the data and compare model performance between them. So for example, here are just like the number of object instances with each of those classifiers, in this case, day versus night. And we can look at the different prediction statistics, like comparing, this is kind of cut off by the bar here, but true positives and false negatives. We can see confusion matrices for each of these classes for both models, ground truth and the model trained off auto labels, right? Where are we seeing false positive, next false negatives, or just class confusion in general? We can see the confidence and metric distribution based off of these subsets, daytime and nighttime. So what's the model confidence for daytime versus nighttime samples? As you might expect, nighttime samples have slightly lower confidence. So again, this just gives us another tool in our toolkit to analyze the performance of our auto labels. And it's worth noting too that model evaluation is something we have in general for any kind of models. It's not purely tied to auto labeling. The idea is when you add predictions to a data set and you evaluate those predictions against ground truth, or if you just want to analyze the confidence metrics of those predictions, you have this toolkit available as well. All right. So again, the core lesson here is the ability to see your data side by side not only when you're performing like auto labeling workflows, but visualization and model performance analysis as well. We're now just including what's really the has been the core bottleneck, which is annotation, is part of an overall automated workflow within the platform. And this is kind of where we're trying to like move the state of the art of the engineering state of the art forward a bit, just as software engineering has gotten more automated over time and had dedicated tooling to integrate with all of the build, test, and release processes of building software. Same thing here, right? We're moving purely beyond like human annotation and seeing how can we take a data-driven approach to auto labeling while still having the proper QA flows in as well. So with that said, yeah, let me go back here. I was about to say we are about ready for our Q&A. And I see that the first question is, how are you getting a negative confidence in night versus day? I imagine we're going back to here. Let's see. Um, that is a good question. I'm not sure. I see it's going below the zero axis here. This might be, I see it's the same for both. I'm not sure. This might just be a function of the graph and the way the graph is computed with like padding on it, but I don't know for sure. That is a good question. Confidence should not be negative in this case. Any other questions? Whether it's in the Q&A or anywhere else. Okay, yeah, sorry, I see the question now in chat. So this is, I think everyone can see it, but I'll read it or summarize it just in case. So the vision embeddings are showing some mislabeled data. In real world case, is deleting that data the only option, or can I reuse it somehow, maybe by manually relabeling? Okay, yeah, so a couple things. Um, One, part of this approach is to make it iterative, right? So um, if data is mislabeled, that's often a function of having a lower confidence threshold, which means increased recall, but also increased false positives, right? The label is incorrect. It thought it was A when it's actually B because we set a relatively low confidence threshold. Yes, so if you're tagging for relabeling, 51 does not include native human like drawn annotation like directly within the native UI. We do have native integrations with tools like CVAT that you can find in the 51 docs. We've had this integration for a long time, and we have documented workflows of like within these workflows, how would you like um, submit labels, sorry, rather submit samples for human labeling. So yes, you can tag samples for relabeling and then submit it as say like a CVAT job, and that can be part of your QA where those labels can be fixed by a human. Second part of the question, if Voxil 51 can um, actually handle classification, is there a reason it's mostly positioned as just vision? Yeah. Um, so 51 is predominantly historically vision. We support images, we support video, we support multimodal visual data like 3D point clouds and LiDAR. Like, so for example, if I were to open, I'll just open this up real quick. If I were to open or if I were to open like the new scenes data set, for example, this will be, I think this will be a multimodal one. Um, right here, this is multimodal data. Now, this is still vision, but because of our support for video, we also support audio. Audio data sets are something we now support as well. So long story short, the platform's growing. Um, Most of our native capabilities are still focused on vision, but we are increasing the number of domains that we support as well. Okay, how is the quality of auto labels on rare categories? Yes. So if you look at the research paper, and I'll actually throw the paper into chat here in a moment. Give me 1 second here. So I'm going to throw this in chat here. I think this should go to everyone. So this link goes to our website where we link the paper. Um, we have found, as you would expect with zero-shot models, the auto labels on rare categories and on the long tail will start to like diminish in accuracy. So like for some data sets like VOC and Elvis, and even like BDD to a certain extent versus like Coco, for example, we did see some diminished performance for downstream models. And that, again, is sort of a logical limitation of foundation models, right? Like when foundation models are trained off massive public data sets of like everyday categories, very specific rare or domain specific classes would suffer a little bit. And sometimes suffer a lot depending on exactly your confidence threshold or what you've chosen. So this is sort of like a continuing research area, and this is also an example where depending on your domain, you might have more human labeled input than others. We really treat auto labeling because we call it verified auto labeling, because we have these curated review cycles. We really want to treat this as an iterative process, definitely a first pass, but also, keeping humans in the loop because again, for very, very specialized data, um, foundation off-the-shelf foundation models can only be so performant. In the case of object detection using bounding boxes, do you have any area-based evaluation results? For example, Coco to find small, medium, large. Um, I would have, yeah. I don't believe we addressed that in the paper. I will take note of your question though. That's a really good question. I'll have to look in our research to see if we addressed that specifically. I can't think of where we may have, but I'm gonna make a copy of your question, Kevin, and I will follow up with you um, on that because that's a very good question. All right, next question. Is the goal of auto labeling for labeling, exploring already labeled data, or to label new data sets or new data added to an already trained label? So the goal of auto labeling, that the fundamental goal here is to auto label. There's a couple ways we could approach it. Like ultimately in a real life workflow, it's auto labeling raw unlabeled data, right? Because if you're an organization and you are pulling in data, whether it's data you've purchased or gathered yourself, or you're streaming data from like, an active camera, the idea here is you have massive amounts of data that you need to quickly label. So the assumption here is we don't necessarily have human ground truth that we're already comparing because the goal in this example is we're not developing auto labeling models. We're supplying the auto labeling models. The goal is to develop downstream inference models based off that auto labeled data. Well, if we already had human ground truth that we know is accurate, we could label based off that ground truth. At the same time, that's not the only thing, right? You can also use it to QA your human labeled ground truth as well, like in that donut example I showed earlier where like, okay, maybe humans weren't as good. This is an example where, and this is a bit of a contrived example, but it's where auto or foundation law models might perform even better, right? And this is an example where we can perform that comparison. And I also want to add one last thing here, and I don't think I necessarily said this outright, but what you'll find in the paper, if you read it, is there are some interesting things about the accuracy of auto labels versus human labels that aren't intuitive. So, for example, with increased recall of auto labeling, even with more false positives, making them like less accurate than some human labeled ground truth, we actually found that downstream models in some cases performed better than even more accurate human labels. It was very interesting. Like the increased recall, even with some false positives, caused some interesting behavior in that case. So yes, basically the idea here is because it creates an arbitrary, not an arbitrary, but like a new labeling field, you can include other labeling fields as well. Um, you can add in new data. We have features like data lens and the arbitrary ability to import data into a data set that you can run these on as well, right? You can choose what you're running auto labeling against and when and in the context of which labels. All right. Great questions. Any other final questions before we close out? We have a minute left. All right. Well, folks, thanks so much again for attending and for your participation. Once again, if you registered for the webinar and you're on the call, you will get a follow-up email that includes this stream, this video. You'll get some additional resources and next steps as well. Kevin, got your question. I'll make sure that that gets followed up on because it's a really good question. But again, if you have any other questions at all, real quick, I'm just going to put this in chat. That is my email. If there's any like specific follow-ups or anything, if and you just want to, it's easier to ask the person who did the webinar, feel free to shoot me an email and ask any questions. I'll be happy to answer or direct you to the person who knows the answer. But that said, thank you so much for your attendance. Be on the lookout for follow-up from us and enjoy the rest of your Tuesday.